The next talk in this session is going to be given by Danny Huang. So Danny is a student at the University of California in San Diego. He is advised by Alex Snoren and Ken Yuxing. And he's going to talk about some way of capturing switch models in high fidelity. So Danny, when you're ready.
Thank you. Hi. I'm Danny Huang. Today I'm going to talk about high-fidelity switch models for SDN emulation. My co-authors are Kenneth Yuxing and Alex Snoren from University of California in San Diego. So suppose you're a manager of a network in a small company and that runs some application that talks to some key value store like Redis. Now suppose one day your boss walks in and he says, we want SDN for application. So you said, fine. So several companies approach you with free samples of OpenFlow switches. And for you, the question naturally is, which one should you buy? Naturally, you want to pick the one that would work best for your application. You don't know yet, so you pick one for now. You say you pick HP switch and run your application on top of it and see how it performs. So details about this workload much later, but what this graph essentially shows is how fast your Redis clients are completing their queries. You're a bit worried, as you can see, that about 30% of the queries never completed. So you decided to try another switch. So now, say, for instance, you plug in the Monaco switch. It's doing much better. Faster clients, fewer losses, great. What about the next switch? You plug in the Quanta switch, and you see, not so great right now. So now you're confused. You have the same topology, same application, same workload, but why do you get so vastly different performances? So you show your boss the graphs as we obtained above, and your boss was like, wow, the Monaco is doing really well. Can we get 1,000 Monaco switches and build a data center of Monaco switches? The problem is that your application works best for one Monaco switch. But would it work? Can we say the same thing about 1,000 Monaco switches? In other words, it is how do you predict the performance of 1,000 switches given only one sample switch, and which vendor or which vendors should you pick for this large data center? So you turn to emulation for help. There are great tools out there that do a great job in doing simulation emulation, such as these. And they would emulate or simulate link delays, buffer sizes, topologies, etc. They're great. But in our case, we're talking about OpenFlow. There's a controller. And these tools aren't just good enough to capture the complex interactions between the controller, the control plane, and the data plane. Well, you said that, well, you could use Mininet, which leverages Open vSwitch that emulates the control plane. But the problem is that Open vSwitch, or OVS, itself is just another OpenFlow switch. And just like its hardware counterparts, it also introduces variations, just like the others. So to recap, the problem is that you're trying to predict the performance of OpenFlow networks. But the problem is that different vendors will have different implementations of OpenFlow, and you get different performance variations. And you could use existing emulation techniques to do it, but they're just not good enough. Either they fail to capture the control plane, like Emulab or ModelNet, or they aren't able to capture the variations between all the hardware switches. So our goal is to be able to predict the performance of OpenFlow networks. Our goal is to build an emulator that would capture the performance differences across different vendors. But before we can start building the emulator, we need to first ask, what are some of these performance variations? Examples include flow table sizes. If a switch has a smaller flow table, it can hold fewer active flows. Fewer active flows, more flows have to go through the controller, slower performance. Or it may be the flow table management policy might be different. Some switches have software tables to buffer up rules that are being installed too fast. Some switches simply don't have software tables. So if you install rules too fast, they're just dropped. Some switches, different switches have different CPU speeds. So CPU is sort of involved in handling the control plane communication. So for slow CPU, you get slower performance in the control plane, and in a way, you get slower performance in the data plane, because the control plane and data plane performance are closely coupled. This is a long list. There are different variations. There are complex interactions between different parameters. But for this talk, we're only going to focus on the switch CPU's effect on the control path delays. So what exactly is this effect? So we go back to this familiar diagram of how OpenFlow works. We have the workload at the bottom, the OpenFlow switch in the middle, and the controller at the top. And for our purpose, we assume the controller runs the L2 learning switch module, which installs a new rule for every new flow. Suppose a new flow comes in. It triggers a packet in because it's not matched. And the controller installs a new rule by issuing a flow mod. And in the end, the packet exits. And since we have the flow we have the rule in the flow table, subsequent packets are matched by the TCAM, and the control plane is not involved. TCAM is super fast, so the data plane is super fast. But in the flow setup stage, it is handled by the CPU of the switch, which can be wimpy at times, and typically it's wimpy. And because of this wimpy CPU, the control plane is typically slow, so you usually observe like tremendous delay in both the ingress and the egress directions. And the ingress and egress delays are particularly significant if you're talking about like short microflows. So to build our emulator, we must first understand what are the ingress and egress delays, so as to build our emulator. And first we have to measure these two delays. So we create this test harness that would help us measure the ingress and egress delays. It has a test server connected to a switch. The test server runs the controller, which installs a new rule for every new flow. It runs the Redis server, as well as the Redis client. What the Redis client does is that it installs, it would create microflows, new microflows every 50 milliseconds. Each of these microflows is effectively a Redis query that requests for a 64-byte value, so it's really tiny flow. We would measure the time taken for each Redis query to complete. We will also measure the ingress and egress delays that occur at the switch. So given this test harness, we're able to generate the workload, and we'd like to observe how different switches would react to this particular workload. So we would swap in and out of the appropriate switches as needed. So this graph is exactly the one that you saw earlier. It plots CDF against the Redis client completion times. Same conclusion, different hardware switches, different performances. But we were at the beginning of the talk, we were like not sure why this is happening. But with our test harness, we can break down this measurement into the ingress and egress delays to figure out exactly why we see these differences. So we first focus on the ingress delay. If we look at the ingress, we can see that they are different. Y-axis CDF, and the x-axis shows the ingress delays. You can see that OVS is doing faster than the others in terms of the ingress delay, and we'll come back to this point later. This is an important observation. So we do the same thing. We look at the egress delay similarly. Again, the y-axis plots the CDF, and the x-axis shows the egress delay. Again, OVS is doing faster, and in this case, it has incurred almost 0 delays. So given the ingress and egress graphs, we can now understand why earlier we get so drastically different performances for our Redis clients. With this understanding, we can now start building an emulator that would capture the ingress and the egress delays. Notice that in both ingress and egress case, OVS is the fastest, and this is a really convenient fact, because essentially we can slow down OVS to be just like one of the hardware switches. So in other words, we can transform the OVS's black line downwards to be one of the colored lines. We're slowing down OVS to be just like the hardware switches. So this is our goal for our emulator. So to implement this emulator, we would ideally slow down the control plane traffic between the controller and the switch. But we don't really want to change the controller or the switch. So we would insert a layer of proxy between the switch and the controller. What this proxy does is that it slows down the packet in events using inverse transform sampling. Details about this in the paper, but essentially the key idea is that if the hardware switch delays by some amount with some probability, we would delay by the same amount with the same probability. We would delay the flow mod event using a similar technique, and in the end, we are able to approximate the performance of the hardware OpenFlow switch in the control plane. So how are we doing in this case? So we evaluate, we measure the HP switch, we put the measurements into our emulator, we put our emulator into test harness. And this graph compares the performance of our emulator versus the actual hardware switch. Y-axis plots the CDF, and the x-axis shows how fast our Redis clients are completing. You can see that the red line shows the hardware performance, and the blue line shows the emulated performance. Essentially, we have slowed down OVS from being the dotted black line to being the blue emulated line. And we're pretty close. And we do the same thing for our, our Monaco switch. We obtain 2 lines, and a Quanta switch. In all 3 cases, we're close. There's a gap between. Still, there's a gap between the blue line and the red line because there are other artifacts that we're not capturing. But given that we've only measured and emulated the ingress and egress delays, we're pretty close. It's a pretty reasonable approximation. So in summary, we have shown that it is difficult to predict the performance of OpenFlow's networks because different vendors do different things about the switches, and you get different performance on different vendors. And we have built an emulator that emulates the control path delays for different switches. And our emulator is simple. It only captures the ingress and egress delays, but it is able to achieve reasonable approximation. There's still a lot of work to be done. For instance, we need to increase the realism. There are tons of other artifacts like flow table sizes or flow table management policies we need to capture. So ideally, we will have to capture more of those. Also, we would like to expand the workload coverage. So if you give me a new switch, I will have to first generate the workload, measure it manually, and plug the measurements into our emulator and repeat the whole process. It would be great if we could automate this process for different kinds of workload. So our emulator will work for different kinds of workload. And finally, we want to capture interactions amongst different switches. So right now, our emulator only works for one single kind of, or rather, our emulator can only emulate one single switch, but it would be great if we can capture interactions between multiple switches and eventually emulate multiple, maybe a cluster of switches. With this, I conclude my talk. Thank you.
Hi, this is Hassan Qazi from LUMS. Very interesting direction of work. One concern that I have is that many of the implementation details are not exposed by the vendors for proprietary reasons. How do you plan to address that challenge?
You're saying that multiple people...
So many of the implementation details, switch implementation details,
Right.
are not exposed by the vendors for proprietary reasons. So how do you plan to address the challenge of sort of capturing that in your emulation?
So this is one challenge that we face too. We see different switches have different performances, and to many researchers, these switches are, like you said, are black boxes, and we don't know what's going on. So what this project does is that it allows you to treat a switch as a black box, and it would only look at the high-level differences, like, say, in this case, the ingress and egress delays, and it would sort of treat it as a black box and model these high-level differences and allow you to sort of capture the differences using simple models.
Sure. I was talking about additional, like flow management policies or flow table sizes and other factors. So when you're focused on sort of CPU and the delays
Yes.
between ingress and egress, there are other factors which are sort of hidden.
Yes, there are other factors. We have highlighted in the paper. Our paper has outlined different techniques for different other different variations, like flow table sizes, but more details in the paper, basically.
We have time for 2 more questions.
From Cloud, and I actually have the similar kind of questions. That do you have any plan for modeling the different performance parameters depending on the flow size or something?
Modeling what? I'm sorry.
Performance difference modeling the from the flow size table or the cache size or some other different models.
Yes, we have plans. So there are some details in the paper about how to model the flow table sizes. So for that, it's relatively straightforward. Basically, you would have a proxy that would sort of stop accepting incoming flows once it thinks the flow table is full. Say OVS can take about 65,000 flows, but say we want to emulate an HP switch that has only 1,500 rules. So it's trivial to sort of have our emulator just stop accepting the installation of more flows once it hits the 1,500 point. So that's one solution to your problem. But
actually, you have.
Sorry, can you take the rest of the question offline?
Okay.
Hi, nice presentation. I have a quick question about. So you seem to rely on a nice model. You said this is a CDF that I want to approximate.
Right.
If you have that CDF, why not simulate? I mean, what's the benefit of emulation?
The benefit is that
yes. Go ahead.
you can run basically real code. For our case, we are running like unmodified Redis, server and clients. So we are.
But the performance model that you devised was based on the Redis requests, no?
The model is based on, I'm sorry?
The client requests. So basically, for the client request distribution, you got these distribution delay.
Right. And I'm sorry, what's the question?
So the model you divide, the performance model you have, you assume depends on the request pattern of a client.
Yes. So yes, indeed, for the graphs we showed, the models only work for a single kind of workload that is like 50 millisecond gaps and 64-byte values. So I mentioned in the future work that we need to sort of expand the workload coverage so that we can do measurements based on a large variety of workloads. Not only 50 milliseconds, but 100 milliseconds, 1,000 milliseconds, etc. So that will be our goal in future work.
Okay.
So that
thanks.
our model will work for different kinds of workload. But right now, it only works for a single kind.
Thanks.
All right, let us thank the speaker again.